Hello. We have talked a lot about recursion and we talked what recurrence relations are. We saw very many ones. We tried to solve some of them. But what was kind of perhaps a little bit unsatisfactory is that we do not really have a good method to solve these recurrence relations. Now, that's not easy in very general cases. So we're going to restrict ourselves to very specific cases, and that's, you see why the title is quite long, and I will break down what all these terms mean. First of all, we're dealing with a recurrence relation, okay? And so I remind you of one that we had, that was the so-called Fibonacci sequence, right? That was a very nice one that we have discussed. And Fibonacci, I always have to think which is one of the things is doubled, and that's the C's. The Fibonacci sequence, remember, is defined by the recurrence relation Fn. I don't want to make my f's like this. Fn minus 1 plus Fn minus 2. And then we said, okay, F0 is 1, F1 is 1. And that lets us start, because now we know what F2 is. F2, I'm going to just write them down, is the result of adding these two, that's S2. And then you add these two and you get 3. And then you add these two and you get 5. And you keep repeating this, and then you get 8. And then so the next one will be 13, etc. But imagine I ask you, what's the 100th Fibonacci number? What's F100? And then you say, okay, I have a lot of time, so I'm sitting home anyway, so I'm going to all do this, and after 100 calculations, you tell me what the F100 is. And then I said, oh, I misspoke. I meant, what is the 100 millionth one? And then you go, oh no. So are there ways of calculating this directly without having to calculate every single element in that sequence? Okay, that we will answer, although it will not be such an easy answer either, but we will do it. Okay, so this is clearly an example of a recurrence relation, but it's actually an example of what this whole title is. Now, I want to emphasize a couple of other terms here. There's a term linear. There's a term constant coefficients. There's this modifier, no, that two color that we can recognize, blue. There is homogeneous, and then there is, let's do brown, quadratic. That's gray or brown, I don't know what that is. Okay. So what do all these terms mean? First of all, quadratic, of course, means degree 2. So what I really need to do here is, this is what we're going to study in this lecture today. So, but in general, we would have here of degree k. So let's first talk about what is this degree here. Well, the degree, remember, what is a recurrence relation is a relation that calculates the values of the sequence by using previous values. And the question is, how far back are we going? So the degree is how far we need to go back. So what does it mean? For instance, in the Fibonacci sequence, we only have to go back to the last two, right? You see here, if I have to calculate this guy here, I only need to know these two. I don't need to know what was before that. So that's why it's degree 2. So I have to go 1 and 2 back. 1 back, 2 back. So this is degree 2. So let me give you an example of a degree 4. That would be an is 7 times an minus 1 plus 3 times an minus 3 minus 5 times an minus 4. Now you say, hey, professor, you forgot an minus 2. Well, it's not necessarily the case that I need all of them, right? In other words, the coefficient there is 0, but what is important is the last one. It's the last one here. So this is the last, or how far back I have to go. In this case is 4. So that's in other words the degree. So this would be a recurrence relation of degree 4. And then today we will only look at those of degree 2, the quadratic ones. And for instance, the Fibonacci is one of them. Okay, that explains this first one here. So the degree that we have now discussed. What are the other things? Let's look at this thing, constant coefficients here. What does that mean? Well, this is an example of constant. What are the coefficients? The coefficients are, of course, these guys here in front of these of the previous elements of the sequence. And what are they? Well, okay, you would say they're numbers, right? Well, but what matters to us that is that they are constants. So constants means real numbers, because we're not working with complex numbers. It's a fancy word, but it brings out a better what it means to have constants here, because let me give you an example of something that has not a degree 2 that is not with constant coefficients. Namely, suppose I have to do this. So we see here the degree is 2, but this coefficient is not a constant. It depends on n, which is a bit annoying, right? Because otherwise I won't, when I'm calculating here in the Fibonacci sequence, as I said, I only need to think about the last two, and I don't even need to keep track where am I in the series. I just add the last two, that's it. Because the coefficients of my relation, the coefficients here of course are 1 and 1, right? So these are the constants here that we normally don't write, so I'm going to erase them again, but just to make it clear that they are there. But if I would have to calculate a series here, then I not only have to, I only need to know the last two, but I also need to know at what stage I am, because I need to know the value of n. And that makes it much harder. So that is something of, this is an example of something that is that does not have constant coefficients. So this is, as I say, a counter example. Okay. Of that, or something that defies the definition. Okay, that's constant coefficient. The next one, linear. What does that mean? Okay, so linear here. So what is linear here? Now this, if I wanted to do first this guy, pink. Okay, these guys here. These are the terms, right? And they are just by themselves. In other words, I haven't squared them, I haven't multiplied them. So these are linear in those terms. So that's what this linear refers to. So linear means that the terms of the sequence all appear linearly. Perhaps it's again better if I give you an example where it is not the case. Let me do another one, Cn. So not linear. So the previous Bn was an example of a not constant. So now Cn here is an example. Cn minus 1 squared plus 3 times Cn minus 2. This has degree 2. It has constant coefficients, because the coefficients are just 1 and 3, but it is not linear, non-linear, because we have squared this thing, makes it non-linear. We have squared this guy. And another example would be, for instance, if I would do, like, say, dn is dn minus 1 times dn minus 2. Now, granted, each term is separately linear, but we multiply them, so the whole thing is not linear. Okay, so this is not linear either, because we have multiplied the terms. So you see, it's already quite restrictive, this thing. And I have not talked about homogeneous yet. So now, what does this homogeneous mean? Well, this is the fact that there's nothing here. Sorry, there's nothing here that makes it homogeneous. What could have been there? Well, suppose I would have something like this. Sorry, the blue. So a non-homogeneous would be if I have something like, again, I do, let's do one of the previous ones, Bn, let's call them E, yeah, let's call them all different names. En is 3 times En minus 1 plus 7 times En minus 2 plus 3n squared. Let's look what we have here. What is the degree here? Well, how far do we have to go back? Well, really only 2, right? So the degree is 2. Okay, this is the last one that I'm discussing, is 2. Be careful, right? Sometimes they might write that one first. It's not the one that is last mentioned. It's the one of the lowest index. Okay, so degree 2. Does it have constant coefficients? Yeah, the coefficients are constant, because the coefficients are 3 and f. Is this linear? Yes, because En and En minus 1, En minus 2 come to power 1. I'm not multiplying, they're really linear, so this is linear. But what we have is this extra term here. So this term here makes it non-homogeneous. Notice that this term does not depend on the series. It depends on n, but it doesn't depend on the series. So even this one, let me do the same guy. En is 3En minus 1 plus 7En minus 2 plus 3. Even this one is not homogeneous, although it's a very simple thing that I'm adding, just 3. But why is it not homogeneous? Because there's a term that does not involve the previous term, the previous element of the sequence. Okay, it's independent of the sequence. In this case, it's actually constant. It could be 3n squared. It could be more complicated. It could be, for instance, instead of 3n squared, I could also have put, or so another example is I put, say, for instance, 3 to the power n. It doesn't have to be polynomial here. It could be exponential or so. And those we will actually solve. So the only thing that we will, what are the things that we're going to, so this is 8.2, but I'm going to break it down in 3 parts. The first part is I'm going to concentrate on the quadratic ones, and then in part 2 I will talk about higher degrees, and then in the last part I will talk about what if you make this homogeneous go away. In other words, what about the non-homogeneous ones? Okay, that's the introduction of what type of things we are looking for. Let's start now trying to solve this. Okay, I'm going to motivate it a little bit by a very simple example that we actually can solve. Let's look at this example. an is 3 times an minus 1. There's another thing I have to discuss, but I'm going to wait until we are there. So what is this? Let's call it degree. The degree is 1. So degree is 1, because I only have to go back 1. Degree is 1. It's linear, because it's just an minus 1. It has constant coefficients, so it all fits one thing, and it is homogeneous, because it doesn't involve anything else. The constant coefficient here is 3. Okay, so it checks out, well, okay, I said we're going to do degree 2, so because these are so simple, I'm not going to do this. Now, one thing I have not really mentioned yet are the initial conditions. I did mention it on an example of the Fibonacci. So now the question is, how many initial conditions do we need in order to uniquely find the unique solution? Namely, remember, if you do not in the Fibonacci sequence stipulate that f0 is 1 and f1 is 1, then you are not able to start. So you need starting values, and you need 2. Why? Because you went 2 back. And therefore, since we said the degree is how far you go back, what we will see is that in this case, we need k initial conditions in order to start off. It makes sense, right? If you have this example here, let's look at this example, and you want to calculate, say, a5, that means you have to know what a4 is, what a2 is, and a1 is, before you can even start. So you need those values to start. Otherwise, you cannot calculate the next one. So that's the number of initial conditions will depend, is exactly the degree. So that's another way that you can think of the degree, is the number of initial conditions that you need. What I say that you need means to find a unique solution. If you do not have an initial condition, of if you relax this, then you have many solutions depending on what initial choices you make. Okay, so in this case, so how many initial conditions do I need? 1. So let's say a0 is 1. Let's take it very, very simple. Okay. By the way, when I say initial conditions, we normally start from 0 and then 1 and then 2 and 3. Sometimes we start from 1. Sometimes we start even from higher indices. It depends on how the sequence, what type of sequence we're looking at. So, but that's not really so important, because we can always renumber a sequence. Okay. So, okay, a0 is 1. And then we can actually solve this, right? Because what is a1? Well, a1 is 3 times a0, which is 3 times 1 is 3. And then a2, well, that is 3 times a1, which is already, we know it's 3, so it's 3 squared. Better to write it this way than 9, because now I see the pattern, right? This is a3, a2, that is 3 times 3 squared, that is 3 cubed. So I know, without much trouble, that this is going to be the general solution. An is 3 to the power n. I can prove it by using induction, and we actually have done examples of that. Good. What you see is actually that the sequence that you get, this has a name. Do you remember this from calculus? This is a geometric series. So if you start from a degree 1, constant coefficients, linear, homogeneous, your solution is actually basically a geometric series or a multiple of that, because why is it 3 to the n? Suppose if I replace this 1 by say 2, what would have happened? Well, everything else would have been doubled. So in that case, my solution would have been a n is twice 3 to the power n, which is not the same as 6 to the power n. Be careful, right? 2 has no exponent here. 2 is just twice 3 to the power n. So you can write it this way. We normally write it this way, but this is a little bit misleading if you don't put a dot there. Okay, so I put a dot there to show you, and that is because I chose 2. And if I took it, because remember, then this 2 would make it 6. Here we would have 6, that would make it twice that. Here we would have twice this. So each time we would have twice as much. Okay. So a geometric series, and that's the clue here. So let's think. Okay, if this is what happens in degree 1, so perhaps the same thing happens in degree 2. So let's look at a general degree 2 constant coefficients. Let's write down how this generally looks like. an, and now we know it has to depend on an minus 1, it has to depend on an minus 2, and those have to be linear, so no fancy powers, no multiplication. And what we're gonna add or subtract, and moreover we have to add and multiply with constants, because that's the constant coefficient part, right? The green, this guy, the linear I've taken care of now. It is quadratic I've taken care of. The homogeneous I made care of because I didn't write anything else. If I put here plus 7, yeah, then I screw that up, but that's for later. So I have to put coefficients here. Now I don't want to write down specific numbers, so I call this C1 and C2. So C1, C2 are constants. Okay, but given constants, we know what they are in particular cases. In Fibonacci's case, they would be, what are they there? 1 and 1, okay? Because the coefficients were 1 and 1 there, okay? So, this is the situation that I'm in. And so now I'm thinking, propose. So what I'm going to say now, so I'm putting here between big parentheses, is a little bit explaining what we're going to do. And then I'll tell you how we're really going to do it. Okay, so propose a geometric solution. Geometric series solution. Let's see what that would be. So the solution I'm thinking of is, let's call it r to the n. Very often that's how we write a rational series, a geometric series, right? And we call r the ratio or the whatever. Okay, so r to the n. So if that would be a solution, if that's a solution of this equation, then if I plug it in, I should get an equality. So let's see what that gives. R to the n, r to the power n, that's an, is c1 times, now an minus 1 is of course r to the power n minus 1, and the next one is c2 r to the n minus 2. So this is the equation I have. Let me simplify this, and I can simplify this because there's a lot of powers of r I can factor out. How much powers of r can I factor out? Well, it's the last one here, right? So let's factor out that. So divide, or let's say divide by r to the n minus 2, both sides. What's the result if I divide? So I'll write it down here that you see what I'm doing. R n minus 2, r n minus 2, r n minus 2. So what's the result? If I divide, remember dividing means subtracting exponents, so in the top I have only 2 left, here I have only 1 left, and there I have nothing left. So we get this equation, which actually, if you think of it as an, remember we don't know r, right? So r is unknown for us for the moment. We don't know yet what r is. I'm proposing it. And so we see that's actually a solution of a quadratic equation, r squared minus c1r minus c2 equals 0. That's a quadratic equation. Quadratic, degree 2, that all makes sense, right? That's why, now you can see that the equation I'm going to get here is exactly the degree of this, what I call the degree of this recursion relation. And so, and I'm not going to spell it out, we'll do it later. This particular one here, that was degree 4, therefore the corresponding equation that I would get would be of degree 4. Okay, makes sense, right? Okay, so this has a name. This is called the characteristic equation. Characteristic equation of the recurrence relation, and it's a very important feature because it gives us solutions. Namely, if I find a solution of this equation, then I have found a solution. But what is now? You say, okay, we're done, Professor. I'm going home. Bye. No. First of all, you should be home already because you're not. I don't know where you're looking. I hope you're not watching this on the subway because that's going to be very difficult to follow. But okay, so no, it's not done because what's the problem? The problem is that at the moment we have a solution, but does it satisfy our initial conditions? Remember, how many initial conditions should we have? This was a quadratic, so we have 2 initial conditions. I have not spelled them out yet because it does not make much sense to write them down if I don't know concretely what the numbers are. But there are also 2 initial conditions. Namely, I would say A0 is such and such and A1 is such and such. Now that might not be my solution that I have here, this r to the n might not satisfy that if I find this particular r. Okay, so how do we do this then? Okay, as I said, all this was between parentheses just to explain now the general technique. Okay, here's the general technique. And I do it on an example. I do the following example. I have the equation an is 5 times an minus 1 minus 6 times an minus 2. Okay, let's analyze this. The degree is 2, right? Because I go back 2. It has constant coefficients. The coefficients here being 5 and negative 6, so that checks out. It's homogeneous. That checks out, right? Because I didn't, if I would put here a plus 4 or something, then yeah, I would screw that up. But we will talk about them. So homogeneous, so fine. And what else was that? Linear, yeah. That's also okay because I didn't took powers of this series or anything like that, of this sequence. Okay, so the characteristic equation. You have to be a little bit careful. How do we get that? Look at what we have, right? We had these constants here, and then the characteristic equation actually is you bring the constants to the other side, so they come with a negative sign. So degree 2 r squared. The book uses small cap r, but my small cap r's are very illegible, so I'm going to use capital R's. Okay, I hope you agree. So r here is a variable, really. It might be something weird for you, but remember, you can give names however you want, right? It's a free country, so we call my variable r here. So r squared, and now I have to bring this to the other side. You could, if you find it a bit awkward, then say 5r minus 6, and then bring it to the other side. So how do I plug it in? That's a good question, right? So it's a little bit, you have to think a little bit what it is, right? It is really dividing. In other words, the lowest, the farthest back you go, that becomes a constant. So the next one, that will become the linear term, and then the last one, the actual one, will be the quadratic term, or later on will get even higher terms. So you have to practice this a little bit on finding, given a recurrence relation, finding its a characteristic equation. Okay, moving on. So r squared minus 5r plus 6 is 0. And I have to solve this. So we're going to solve this characteristic equation. Solve for r. Okay, that's factoring. We only do factoring. R minus. Okay. I told you r is a variable here. You might think always, you like to prefer x, but let's do r here. So 2 numbers that multiply to 6 and add up to negative 5. I found them. Okay. So I find r is 2 and r is 3. So what does this already mean? From our previous discussion, we know that 2 to the power n will be a solution. 3 to the power n will be a solution. Simply just because of our calculation here. Go back to it. In other words, basically we do the argument that way, and you'll see we do get a solution on this recurrence relation. So 2 different solutions we have already, but we still have initial conditions. I haven't said this, sorry, I should have said this. And a 0 is 1 and a 1 is 2. I'm picking something. That doesn't mean matter what to do. So let's see, does this guy satisfy my initial condition? Yeah, actually it does a 0, because 2 to the power 0 is 1. But it doesn't do with, oh, it does actually the second one too. So that's a bad choice. Okay, I'm going to put 5 here. A1 is 5. So now if I put it n equals 1, then it doesn't satisfy it. The previous one actually 2 to the n satisfied it. That was a bad choice. And the same is true for Rn, right? 3 to the n. If n is 0, I get 1, so it satisfies the first initial condition, but it doesn't satisfy the second. That's a bit of a problem. So how do I find a general, the correct solution? Well, that is by the assumption that I'm going to make the following assumption, and that I'm allowed to make the following statement: the solution will be a combination of these two, a linear combination. It means there will be alpha 1 to the power n plus alpha 2 3 to the power n. So I take a linear combination of this function and of this function. Okay. Now linear means that alpha 1 and alpha 2 are again constants. I don't know, I would have not used Greek letters, but the book does it, so I'm sticking with what the book does. Okay. You say, okay, professor, but now what about this alpha 1 and alpha 2? That's it? Just their constants? No, they are particular constants. They are very, very specific constants, but we don't know yet what. How do we find the constants? So this was, if I should have put perhaps in steps, right? Step 1 was find the characteristic equation. Step 2 is solve it. Step 3 is proposing a solution. And now step 4 is determine alpha 1 and alpha 2 using the initial conditions, because that's something we have not really used yet. We checked it and we saw that what we found was not the solution, so we have to get it better. Okay, let's do this. So what does that mean? A0 is supposed to be 1. So what is if an, so this is the proposed solution, right? I propose that an is of that. Okay, so that would be alpha 1 2 to the power 0 plus alpha 2 3 to the power 0. That would mean alpha 1 plus alpha 2. But there's a second one. A1 is equal to 5. That would be alpha 1 2 to the power 1 plus alpha 2 3 to the power 1, right? Because n is now 1. That has to be equal to what? To 5. Okay, so what does that mean? That means 2 times alpha 1 plus 3 times alpha 2 is 5. We get a linear system of equations in two unknowns. We can solve that if you have taken or are taking linear algebra. You can do this using matrices, but we have learned this also before, that there are different methods. We can do the method of substitution. We can do the method of cancellation. I'm going to do just substitution. What does it mean? I take one of the equations and solve for one of the variables. So let's take this equation and I write that alpha 1 is 1 minus alpha 2. And then I plug this in here and say that 5, remember this is what it is, right? 5 is equal to 2 times alpha 1, which is 1 minus alpha 2, plus 3 times alpha 2. And so what I get, 2 minus 2 times alpha 2 plus 3 times alpha 2. So I get 2 plus alpha 2, and then if I bring this to the other side, I find that 3 is equal to alpha 2. Okay, so alpha 2 is 3, and then how do you find alpha 2? Well, now you plug it back in there. Okay, this is the method of substitution. So in other words, what you do is solve a linear system of equations, and that's something I'm going to let you review for yourself. Okay, I just did it here, and there's another way, right? But I'll do this one. Perhaps I'll show the other way at some other point. Okay, so what we have here, alpha 1 is the 1 minus 3, that is minus 2. Okay. So what do we have now? Let's see. We have alpha 1, we have alpha 2, so our solution, here's the solution. An is equal to negative 2 to the power n plus 3 times 3 to the power n. Negative 2 and 3 are the coefficients here, the alpha 1 and alpha 2. that at the beginning I didn't know, but now I know. And be very careful, right? I'm saying these are coefficients. They are not to the power n, right? Don't try to simplify this by combining minus 2 and 2. This is not minus 4 to the power n. This is minus 2 times 2 to the power n, plus 3 times 3 to the power n. So that's the solution, and you can check now that A0 is what it is 1, and A1 is, you can always double check if you do a quiz or something like that you have actually the right numbers. And it also satisfies the recurrence relation, again something you can check. Okay, let's do another example quickly and go a little bit faster on this one to show you that other things can happen. Not other things, but something special, something we might be a little bit surprised by is, let's look at this. I take this from the book, where A0 is 2 and A1 is 7. Okay, so let's look at what we have here. Step 1, the characteristic equation. So from now on, it's all calculating these things, right? So what is the characteristic equation? I'm going to write it down and let you think about it. Is this the correct way or not? Okay, I brought so if you want, you can write it first as r squared is r plus 2 times plus 2, sorry. This one I get rid of, plus 2. Right? Just make sure that you understand how I get this characteristic equation, because they're so important. Okay, so that's my characteristic equation. Then step 2 is solve it. We factor this as r, let's see, r minus 2 times r plus 1 is 0, right? Is that correct? Yes. Okay, so this means the two roots are r equals 2 and r equals -1. Step 3, I propose solution. An is equal to this guy to the power n with a certain coefficient, alpha 1 2 to the power n, plus this guy to the power n with the coefficient alpha 2. But minus 1 to the power n is actually just plus a minus 1, so this is a bit special here, but okay, let's try now on. Step 4, the initial conditions. So determine alpha 1 and alpha 2 using initial conditions. So the first initial condition is A0, that was, what was that supposed to be? 1, right? Yeah, no, 2. It's 2, so that is, if I plug this in here, alpha 1, and this is plus alpha 2, right? Because the powers are 0. Alpha 1, that was equal to 7, so this would be 2 times alpha 1, if I put in 1 here, and if I put the 1 here, I get the negative, right? Minus alpha 2. So here I can do substitution, but there's a method of elimination, or what I do is add these two equations. So I'm now solving, right? So I'm solving this system of equation. And one way I can do is add these two. So add this equation to the other one to get A0 plus not A0, these two guys. 2 plus 7, so 9 equals. Why do I do that? Well, this is 3A1, 3 alpha 1, but these two cancel out. So that's what elimination does. You try to cancel out one of them. So 9 is 3 alpha 1, so we see that alpha 1 is 3. And once you have one, you plug it in one of the previous ones that you have. So I can plug it in here. 7 is 2 times 3 minus alpha 2. That is 6 minus alpha 2. So if I bring this to the other side, that is 1 is equal to minus alpha 2. So alpha 2 is equal to minus 1. And so the solution is an, the solution is an is, what was it? 3 times 2 to the power n minus 1 to the power n. Okay, and so if I would now ask you what is A10, you can plug it in. A10 would be equal to 3 times 2 to the power 10 minus 1 to the power 10, that is 1. So this number. Okay. And so you see actually that the solution here is actually basically powers of 2 with plus or minus 1, because this term is always going to be plus or minus 1. Okay, so this is the feature that you sometimes see in this kind of solutions. Okay, now I want to do the two things we need to discuss still, and one of them I'm going to discuss in the next one, because it's more the general case. It is a quadratic case, but what in case we have twice the same root? Okay, we had two different roots, and then we got two different solutions. But if I put here twice the same thing, that's not going to give me anything new. You say, okay, so that means there's only the geometric series is going to be an answer. No, that's not going to work. I need two different solutions. I need to take a linear combination of two solutions because it's a quadratic. And therefore, if I do something of degree 3, I need 3 different solutions to build all possible solutions. Okay? I'll say more about this next time. So I'm not going to talk about this case because I don't want to make this too long here. But what I do want to do now is a Fibonacci sequence. It is a little bit uglier, but it is instructive. Okay, so Fn is Fn minus 1 plus Fn minus 2. And this is F0 is 1 and F1 is 1. Okay, characteristic equation. I'm going to go a bit quicker here. R squared is R plus 1, so R squared minus R minus 1 is 0. Now, this cannot be factored simply, so I have to do the quadratic formula. So the quadratic formula is R is equal to minus b, so minus b plus minus radical b squared minus 4ac over 2a. Now a is 1, so that makes it easy. So r is equal to minus b, so 1 plus minus b squared 1 minus 4 times 1 times minus 1. I hope you see it's 5, and then in the bottom I have 2. So r, there are two solutions here, 1 plus radical 5 over 2 and 1 minus radical 5 over 2. Now you say, oh boy, these are ugly numbers. If you ask an statistician, an architect, anybody that is interested in arts will say these are the most beautiful numbers in the world, because these are the so-called golden ratio. And this is a very important aesthetic feature that, and also in nature we see it happen, just naturally occur, because it gives the best, the most nicest, pleasing to the eye ratio of, let's say, the height of a building versus its width. If you make a building very high and like this, you get kind of a skyscraper. If you make it like this, it also looks lovely. But if you make the ratio something like that, the width of the house is times this number is the height of the house, you get something that looks very pleasing, looks very quiet, very natural. This is what we call the golden ratio. But that is just something. Is this an accident? Well, I don't know that this is an accident, and in fact I have seen people explain this as not being an accident. That the reason that these numbers are that we get the golden ratio here is very strongly related to the Fibonacci sequence, and in fact even there are explanations I've once heard to talk about this by a biologist. They said that in nature, leaves and flowers and plants prefer this kind of Fibonacci sequence, and therefore the golden ratio. Now, going on. What is our general solution of the Fibonacci sequence? Well, this is the r's, right? So we have to take this number to the power n. That would be one of the solutions, and the other one would be the one with the negative. So this is how the general solution of... That's ugly, right? But okay, that's not the solution. We have to now find the initial conditions. Let's look what they are. Now, I don't know whether you've already noticed, but the first initial condition is actually very pleasant, right? Because you take the power 0, that is just 1. So we get alpha 1 plus alpha 2, and that was equal to 1, right? The second initial condition was also 1. Now we have something a little bit uglier. 1 plus radical 5 over 2 plus alpha 2, 1 minus radical 5 over 2. Okay. Now I'm gonna write this out a little bit. Okay. So that is I'm gonna split off the radical 5. So we have alpha 1 over 2 plus alpha 2 over 2. These are the parts without the radical, and then the parts with the radical is alpha 1 radical 5 over 2 plus, or rather minus alpha 2 radical 5 over 2. Okay. So this is alpha 1 plus alpha 2 over 2 plus alpha 1 minus alpha 2 times radical 5 over 2. Okay, now alpha 1 plus alpha 2 is actually 1, so actually this whole thing is just a half. Now remember, the initial condition was 1, so 1 is equal to a half, and we get that this is equal to alpha 1 minus alpha 2 radical 5 over 2. Okay, sorry, plus, there's a plus here, sorry, but equals, there was a plus. Bring the half to the other side to get a half is equal to alpha 1 minus alpha 2 radical 5 over 2. We can even get rid of the 2 here, so we get that 1 is equal to alpha 1 minus alpha 2 radical 5, and 1 is equal to alpha 1 plus alpha 2. Now, I'm not going to solve this exactly for you, so dot dot dot. So at home, just work this out. It's really simple, but it gets a little bit, with the radicals, gets a little bit ugly. The solutions are actually 1 over radical 5, and alpha 2 is minus 1 over radical 5. So, what does this mean? This means that the Fibonacci series is given by the formula. Alpha 1, 1 over radical 5, that was a coefficient of this guy. And let me scroll up. If you don't believe me, that's what it was, right? And alpha 2, that's minus 1 over radical 5, is 1 minus radical 5 over 2 to the power n. That's it. So if I ask you what is F100, you plug this in. Now you're going to say, Professor, this is impossible. There are radicals there. Look at your Fibonacci series here. I don't see any radicals. What happens here? Where is it? Where is here? These are all nice numbers. Okay, they get a bit bigger. 21 is the next one. And then what is it? 34 or something. And you keep working. But what the hell? Where are these radical 5s? None of these cannot be, because we're adding two natural numbers. It should be a natural number again. There can be never radical 5s in it. So the answer is, no matter what n you plug in, the radicals will cancel. Cute, eh? These radicals just will cancel. Although it's not obvious at all, even for 2, to see that they cancel, you have to actually work it out. So F2, for this formula, I leave it up to you. Use this formula and convince yourself that the answer is actually equal to 2. You would not believe that, right? If you would see this formula, you would say, oh, that's a horrible number, I'm not even coming close to it. But actually, for n is 2, it comes out nice. For n it's 100, it also comes out, but it's not so easy to calculate anymore, because you have to take 100 powers. And that is a very comical thing too. But I should say, from an algorithmic point of view, from a calculation point of view, it's much easier to calculate this. So a computer can be made to compute this very quickly in polynomial time, whereas if you would have done the recursion relation, we'll talk more about complexities of recursion relations, that would be much worse. So knowing the solution can make it much easier to calculate these elements in this series, in a geometric series, in a recurrence relation. Sorry, not in a geometric series, I mean in a recurrence solution of recurrence relations, rather than actually calculate them by just hand or by using the recursion itself. I've said this before, and we'll come back to it. Recursion is a very strong, powerful way of saying something, making very complicated things by very simple equations, but solving them can be very difficult, and you might need different techniques, like the one that we discussed just now, to solve actually them. Now I'm going to stop here, and as I said, one thing that I still have to do this, so I didn't do all the quadratics, but we'll do that next time. And then we also look at higher degrees. Degree 3 perhaps is the highest we'll ever really go. But I will tell you how it works in general, and there we will even already kind of have to limit ourselves a little bit on what we will or can do. Okay, that's for next time.